In this video, we're going to explore how we can use the second derivatives in a new way, and we're going to do it in analogy to what we've seen earlier in the course by building Taylor polynomials. We've already seen the tangent plane, or linear approximation formulas, written out like this. And remember that we had an analogy for that back in single variable calculus. It was just this part here. But in single variable calculus, we also were able to extend this by adding a quadratic term or a cubic term or a fourth order term. And that's what gave us what we called Taylor polynomials. What we're going to do now is do that same extension, but now include another variable as well. So this expression here is what we called one time the local linearization of f. We also called it the equation of the tangent plane to the surface at that point. And we can also think of this as a degree 1 Taylor polynomial. There's no quadratics, there's linear terms though, so it's degree 1. We would immediately see, if we had some kind of curved surface, that there's limitations to a tangent plane approach. If we draw a tangent plane and try to use that as an approximation to the curved surface, it's not great. The surface itself is not flat, except when we look really, really close. But then the question might come up, what if we fit some kind of quadratic shape to that? Then it would actually have the same curvature as our surface. Well, now we would have a better approximation, more accurate for longer distances, and we can see how we could extend this idea simply by adding a quadratic term or more, one or more quadratic terms on the end. Let's take a stab at that. If we imagine our function being approximated by a quadratic Taylor polynomial, well, we know we're going to have, by analogy from the fall term, or the first half of the course, x derivative times x minus a, y derivative times, at the same point, ab times y minus b, remembering that when we did quadratic Taylor polynomials before, they included all the linear terms plus some more stuff. And then, well, we can see already that we might want a second derivative like we had originally with the first variable or single variable formulas. And the form that went with that was x minus a squared. Well, that seems pretty reasonable here because we have an x derivative. We have a partial x derivative twice. And we might then want a mixed, go back. And if we have a y variable, well, it seems silly to just do this for x. Y would have the same kind of impact, but the form would be essentially identical. Now the only tricky part is we might actually have something about the mixed partial derivative. We take the mixed partial derivative at the same point, and instead of just x squared or y squared, well, we have x and y in here, so maybe not surprisingly, we have a mixed multiplier here as well. And so there's a lovely structure to this. One derivative of x, one x multiplier. One y derivative, one y multiplier. An x and a y derivative, an x and a y multiplier. Now, that's very, very close. Now there is one last correction. When we had these terms with single variables, you might remember that there was a coefficient of 1/2. And that actually applies to both of these terms here. But surprisingly, not surprisingly, it is different, unfortunately. The multiplier for the mixed partial derivative is just 1. It's not 1/2. If you want the short version of why that occurs, think about differentiating this term here. You'd get a 2 down, and we put this 1/2 in essentially to cancel that 2. We differentiate this, the 2 comes down, we'd cancel the 1/2. When we have the mixed partial derivatives, there's no 2. We just get 2 1s as we differentiate, and so we don't need to cancel anything, so there's a 1. That's essentially the argument. To prove it more consistently or more strongly, it's about a page and a half of algebra, but that's what it boils down to. So if you're looking for a mnemonic, look for the powers up here and have 1 over that power out front. Let's do an example here just to see how this all plays out. Our function is fairly complicated, cos of 3x times y squared outside. And if we take a look back at our formula, we're going to need the single derivatives, first derivatives, and all three of the second derivatives. So we might as well put these all out. I'm going to skip the xy notation for the remainder. We know these are functions of x and y. And just for compactness, write the subscript derivatives. So we're going to take the x derivative of this, and that will give us negative sine of 3x times derivative x of the inside times 3 times y squared. Then we take the y derivative, and just be careful where we're going from. We're going back to the original function. And so we take the y derivative of that. It's just the external y squared. The 3x is a constant multiplier. So we get cos of 3x times 2y. We then follow up by finding each of the second partial derivatives. And that's the combination of xx, yy, and xy. What we do here is we take the first x derivative and take another x derivative after that. So a partial with respect to x here. And if we scan across, the only x in this formula here is in the inside of the sine function. So we just differentiate the sine to get cos and multiply by 3. And then we multiply that by the existing 3y squared. Going to the yy, same idea, except now we take a y derivative of this term. Cos 3x is a constant. And 2y, when we differentiate it, simply gives us 2. Last but not least, we can find fxy through two ways. Let's take the y derivative currently and differentiate it with respect to x. So we've taken the y derivative already. We'll take the x derivative next, and that means we're going to have negative sine of 3x times 2y, except we have to be careful. When we take the x derivative of the sine function, we also get a 3 multiplier. And then we attach the 2y at the end. It's important to note that if we did the same calculation starting with x, but taking the y derivative, we'd end up with negative sine of 3x, check, times 3, check, times the y derivative of y squared, which is, of course, 2y. So it doesn't matter how you get to the xy derivative, as long as you take one x and one y derivative in some sequence. After that, we evaluate this at the point 0, 1, because that's the location where we're trying to build our approximation. So we simply sub this in, and we remind ourselves that cos of 0, x is going to be 0, cos of 0 is 1, sine of 0 is 0, so we can scan across and get the function value at 0, 1, cos of 1, 0, sorry, cos of 0 is 1, and y squared is 1, so this is all 1. And then I won't put the point in, but we're using the point for each of these calculations. We see sine of 0, that's just going to be 0, times some other stuff, but times 0 doesn't matter. Then cos of 0 times 2y, cos of 0 is 1, so we get 1 times 2, that'll be 2. Then the second partial derivatives, xx will be cos is 1, minus 3 times 3 is minus 9. Fyy will be 1 times 2, which is 2. Sine is 0, so we get 0 there. And then we are ready to build our approximation. The function fxy is going to be approximately equal to 1 plus 0 times, that's the x derivative, it would be x minus the x-coordinate where we built our estimate, which is 0, plus the y derivative times y minus 1, and that includes all of our linear terms. Then we go to the quadratic term, so plus, I won't put the dividing line because this is all one expression, plus the 9, well it's negative 9 though, times x minus 0 squared, plus 2 times y minus 1 squared, plus 0, x minus 0, y minus 1, quadratic, 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 but mixed. And then the only thing we can't forget are the multipliers for the quadratics. There's an exponent 2 here. We'll have a half coefficient out front. Same here. And then this term Doesn't really matter because we're multiplying by 0. But if we had a non-zero value, we would just multiply it by 1 or leave it the same way as it is. And if we take all that and tidy it up, we could easily summarize that as 1 plus 2y minus 1s minus 9 halves x minus 0, well that's just x squared, x minus 0 squared, and then the half and the 2 here cancel, plus y minus 1 squared. With that form, we can clearly see the quadratic structure of this polynomial, but we see that it's a mix of x's and y's, and that would have the same curvature and slopes as the original function, this one here, at the point 0, 1.